Hello folks, and welcome to this lesson on primary cells. By the end of this lesson, you should be able to explain how a redox reaction is used to produce electricity in a primary or voltaic cell, and explain the direction of electron flow from anode to cathode in the external circuit and ion movement across the salt bridge in a primary voltaic cell. Now, before we talk about voltaic cells and how they work and how you put them together, let's talk a little bit about how these redox reactions can happen. So if you remember, a redox reaction is a reaction where you have a reduction reaction and an oxidation reaction. And because it's two reactions that are happening at the same time, you can actually do some funky things with that. So let's take this reaction where we're going to take zinc and react it with copper 2 sulfate. Now, based on things that you know from before, you know that zinc is more reactive than the copper, and so this reaction will occur. So the usual way that you would make this reaction happen is referred to as direct electron transfer. And direct electron transfer is basically where you take a stick of zinc and stick it into a beaker of copper 2 sulfate, and then the reaction happens. When you have that happen, the copper is going to form a layer on that piece of zinc, and some of that zinc is going to go into solution until you get to a point where the reaction can't happen anymore, either because the zinc is all gone or the copper is coating every surface and the zinc isn't really accessible to the copper 2 sulfate anymore. But that is not the only way that you can actually have this reaction happen. So remember, a redox reaction is a reduction reaction and an oxidation reaction. And what's happening is that electrons are being transferred between the two reactions. So what if we take those two half reactions, physically separate them in terms of the other chemicals themselves, but then we just allow the electrons to transfer? And that's something that you can do. So you can set up one beaker or one container where you have one of the half reactions, all of the things for one of the half reactions, and then you set up another space where you have all of the things for the other half reaction. We know based on this reaction that oxidation is going to happen on this side, and so when that happens, the electrons will go from, when zinc becomes a zinc ion, the electrons are going to be released. And if we connect this with a wire, these electrons can move over here, where now we can have the reduction reaction happen. In this reaction itself, there is nothing that requires that zinc and that copper to be in the same place. The only real interaction between them is the fact that one of these reactions release electrons and the other one has to take them. So, yeah, this is something that can happen. And we can very much take advantage of what's going on here because now we have a way to make electrons move. Electrons moving is basically electricity. We're making electricity using this redox reaction. So we're going to spend pretty much this entire learning outcome on talking about indirect electron transfer. So first off, let's go through a little bit of terminology. First terms that you're going to need to know is anode and cathode. So we split our two half reactions into two separate spaces, and so each one of those are going to have a name. The anode is the place where oxidation happens, and the cathode is a place that reduction happens. There are plenty of ways for people to remember how these names come about. For me personally, my favorite one is you have anode and you have oxidation, and both of them are vowels. That's usually how I remember how that one works. Now, another thing to go over is the fact that if you need to describe a cell, you're going to have the anode, you're going to have the cathode, and then you have all the different components to it. There is an easier way and a much simpler way to talk about all of that information, and that is cell notation. So in cell notation, you're going to be talking about both the anode and the cathode and what it's all made of. So first thing is that you're going to see some lines. This double line separates the anode and the cathode. So the anode is going to be on the left and the cathode is on the right. Now, with these cells, you're pretty much always going to have something that is solid and some kind of solution. So you do have a variety of different types of materials, and they're all going to be in different phases. So the single lines are those phase boundaries where they indicate that on either side of this line, you're going to have things that are in different phases. So solid, aqueous, liquid, gas, whatever it's going to be. So in this case, you can see that our anode has the reaction, half reaction, where our lead becomes a lead plus 2 ion. You can also include information like the concentration if that's relevant. And then our cathode, it looks a little bit funny because we have 2 ions in the cathode and then you have another metal. So in this particular case, our platinum is what's referred to as a passive electrode. It's not actually involved in the half reaction, but it is a site for everything to happen. This is going to be there are other metals that can also fulfill this role, but it's always going to be something that's very unreactive, but also conducts electricity very well. The reduction reaction itself is between the iron 3 plus and the iron 2 plus ion. So the iron 3 plus ion is going to gain electrons and become iron 2 plus. Now we still need that inert electrode because you need to connect everything together with wires, and so you need something solid to literally connect everything. And so that's why we have this, and then the iron 3 ions are going to react on the surface of that platinum. That's where they're going to get those electrons from. So there are many different types of cells that exist. In this particular lesson, we're going to focus on primary cells, also known as voltaic cells, based off of Volta, who is the Western scientist who is known to first come up with the idea or discover how this all works in the Western world. There are several must-haves that a primary cell has to have to be a primary cell. The first thing is that the redox reaction has to be spontaneous. There also needs to be a physical barrier blocking that direct electron transfer. Otherwise, you're not going to have the electrons traveling through the wire. The transfer would just happen on the surface of everything that's happening, like that whole stick zinc into copper 2 sulfate situation. There also has to be an external electrical circuit. So this is that wire that goes outside of everything. That's where the electrons travel. You need it for that electron travel and to take advantage of it. You also need a means to complete the circuit. So remember that circuits have to be, well, round. You can't have everything going in one direction. At some point, things are not going to stop working. So you need a means to complete the circuit, and we'll talk a little bit more about that in a little bit. And you also need ions present in the solutions, also related to completing that circuit bit. So I want you to pause the video and write down what's here. I'm actually going to not explain any of this right now. I'm going to explain how to sketch these primary cells using an example. All right, this is a cell that we're going to be looking at. We're looking at that aluminum and nickel. We're going to have the aluminum at the anode and then the nickel at the cathode. So first thing that you need to do is sketch your apparatus, the physical substances in which everything is going to happen. Now, I'm going to do most of this drawing using 2 separate beakers, but give me a moment and I'll talk about your other options as well. So in some cases, you might have a setup where it all looks like it's in one container, but there is a barrier between them. Or there's another situation where you can have a larger beaker and then something along the lines of a test tube that has a hole at the bottom. Now, something about both of these is that you still need a physical barrier between your 2 half reactions. So you can see a physical barrier here, and it looks like there might not be here. But you actually would plug up this end of the test tube. So the next thing that you need to do is label your anode and cathode. Don't forget to state which one is which and also the charges as well. And you also want to label what the electrodes are made of. Now, whenever you see anything that I draw, I'm always going to have the anode on the left side and the cathode on the right side. That's just for my ease. It's how I keep track of everything and make sure I'm being consistent every single time. Now, the anode is going to have a negative charge in a primary cell, and the cathode is going to have a positive charge at the, or rather in an primary cell. These charges may be different depending on the type of cell that you have, but the reduction reaction is always going to happen at the cathode, and the oxidation reaction will always happen at the anode. So no matter what those charges are, the type of reaction is always going to be consistent. Next, you need to show the movement of your electrons, and you're going to need to show them in 3 places. At each of your electrodes, and also the direction it's traveling through the wire. This is going to be important because that gets forgotten quite a bit. Make sure your arrows are in the correct directions. You can see here aluminum is becoming the ion, and 3 electrons are being released from the aluminum. And here your nickel ions are becoming the nickel, and then the electrons are combining with those ions to get your nickel metal. You can also write your half reactions underneath the whole thing. Probably a good idea and usually expected. Now the last bit is you need a way for ions to be able to move. Because take a look at what's happening here. You have your aluminum becoming aluminum ions, and as this reaction keeps on going, this beaker, is going to become more and more positive. There are going to be more and more cations in there just building up. And remember, things of like charges repel each other. And on this side, it's going to become more and more negative because you're removing those cations from solution. So the same idea, these reactions, if nothing else is done to them, are going to stop well before you actually run out of this aluminum or you run out of those nickel ions, because of the fact that you have all this repulsion going on. You have all these charges building up, and it's going to stop the reaction. So you need something to help make sure that ions are going to be able to move and replenish what you're missing, so to say. And so that's where the salt bridge comes in. This salt bridge, if you have this 2 beaker situation, is a literal tube that you're going to fill with a salt solution. One of the most important things that you need to consider when you're deciding what salt to fill your salt bridge is that it cannot form a precipitate with anything else in any of your cell. Because if it is forming a precipitate, that means you're now taking things out of the system. It's not usable in this redox reaction at all anymore. So for that, you're generally going to want to use a group 1 cation for the cation part of your salt, and you probably want to go for a halogen or something of the like for your anion. Nitrates are very soluble with everything, but there also is the issue of nitrates being oxidizers, which means you might get some other reactions happening, which you don't really want. Now, another easy way to decide what you're going to put in, especially for that anion, is take a look at what these solutions are. It doesn't refer to it in this particular case, what the anions are going to be when you're making these solutions, but there always is going to be an anion. And so if you have a specific anion, it's probably because that's what's soluble with it. So take a hint from that. Now, last thing you need to do is label which ions are going where from that salt bridge. So remember that your cations are being used up on this side, so the cations are going to go this way. The cations are building up on this side, so you need more negative charges, and so the anions are going to come this way. Now, one last thing that I'm adding in this particular case that you probably would add in the beginning is just which solution is being used in either case. And then something else that I wanted to mention in terms of these alternative situations is, okay, so this is a setup, these are alternative setups that I can have. How does the Saltbridge thing work? Well, you don't have to use Saltbridges in these particular cases. In this particular case, what you do is you make sure that these boundaries are porous. So it is a solid substance, but particles are able to travel through it. So something like this, and we do have these test tubes that have those holes at the bottom. Something that you can make is an agar solution that you dip the tip in. Once it solidifies, you have a porous membrane there, and the ions can travel right through that agar itself. Now, ashamedly, I have forgotten something from step 1, and that's the fact that you want to include a voltmeter or something else, usually for different types of cells, in that wire. So, here you go. That's your lesson on primary cells. The drawing aspect of this is going to be very important, so make sure you get practice on that. That's the end of this lesson. I'll see you next time.